Welcome back to the deep dive. So if you spent any time at all looking at, the big shifts happening in tech lately, you've seen the words
Oh, yeah. Deep learning,
neural networks.
back propagation.
Right. And if you're like most people, you probably, you instantly picture this chalkboard full of just terrifyingly complex equations.
It sounds completely abstract, something that's only for, people with a PhD in computer science.
Exactly.
And look, while the math behind it all is certainly advanced, the actual process, the fundamental idea of how these things learn, it's surprisingly intuitive.
It's just practice.
It's
Right.
codified practice. That's
Right.
a great way to put it. It's just turning trial and error into a stable, repeatable algorithm.
And that's really our mission today. We've gone through a whole stack of sources explaining these concepts, and we're just going to pull out the most important bits for you.
But we're going to try to turn that messy technical jargon into something you can actually, grab onto.
Using a surprisingly simple analogy, just perfecting a pasta recipe.
The goal here is for you to walk away not just knowing the terms, but really getting the mechanics.
Yeah.
A neural network doesn't think like a person. It follows a very predictable process of making the mistake and then correcting it.
Okay, let's unpack this. So, deep learning, at its core, is just learning through structured practice and feedback, like a chef.
A chef perfecting their signature dish. But before they can even start cooking, they need to get the kitchen ready.
You need a clean, organized, properly measured kitchen. You can't have flour over here and spices somewhere else.
And that brings us to the very first crucial stage, data preparedness. In the real world, information is just chaotic.
Like a picture is just a bunch of colors and light data.
Exactly. And before a network can learn from that, we have to impose some kind of structure.
You can't just toss flour, water, and spices on a counter and call it cooking. So that first step of creating order is called vectorization.
Right. Vectorization is all about translating that chaotic reality, an image, a sentence, whatever it is, into a clean, structured numerical format.
Something the model can actually read.
It has to be numbers. The network can't learn from a picture of a cat. It can only learn from a big array of numbers that represent the cat's pixels.
So we're taking the tomatoes, chopping them, and measuring them precisely.
We're converting the idea of a tomato into a numeric vector.
That translation is so key. Okay, so vectorization changes the form of the data, from messy reality to clean numbers. But even then, you still have a balance issue, which brings us to the next idea, normalization.
Imagine your recipe needs, say, 2 grams of salt, but 5 kilograms of water.
Right.
If you just fed those raw numbers into a model, the water input would be, 2,500 times bigger than the salt input?
And even if salt was the most critical part for the flavor, that huge number for water would just completely overwhelm everything else.
Precisely. The sheer magnitude biases the learning process from the very beginning. So normalization is just scaling those inputs sensibly.
Making sure everything is in a comparable range.
Yeah, often between 0 and 1, or -1 and 1. It's making sure we use 1 teaspoon of salt, not a whole cup, and a normal portion of pasta, not 5 kilograms.
This sounds simple, but I'm guessing if I forgot to normalize a really important feature, the model would it would be incredibly unstable.
Oh, totally. It would bounce around wildly. It wouldn't know which features actually matter because the ones with the biggest numbers would just seem the most important whether they were or not.
Balanced ingredients, balanced data.
Stable learning.
Okay, so our ingredients are prepped, they're translated, they're balanced. Now we can actually start cooking. And as soon as the cook starts, they're making choices. In a neural network, these adjustable choices are called the parameters.
And there are 2 really critical parameters that the network adjusts all by itself as it learns. The first are weights.
So in our pasta recipe, weights would decide the importance of each ingredient.
Yeah.
If I turn up the weight on salt, the dish gets saltier. If I turn down the weight on oil, it gets less rich. The cook learns, maybe I need more herbs and less salt.
That's it. A weight is really just a multiplier. It controls how strongly any given input affects the final outcome. It's the main lever the network pulls to learn things.
So if a network is learning to identify a dog, it might learn to put a higher weight on the shape of the ears than on the color of the fur.
That's a perfect example.
That makes total sense for importance. But then the sources also talk about bias. If weights are doing all the heavy lifting on importance, why do we need bias? What does it do?
That's a great question. Bias is for when you need to shift the entire output, no matter what the inputs were.
Sure.
Imagine a chef who just instinctively always adds one final tiny pinch of salt to every dish,
Mm.
just to make the flavors pop.
Oh, okay.
That's the bias. It's
Yep.
a little adjustment added at the end to fine-tune the balance and get the final result closer to the goal.
So weights control the specific influence of each ingredient, but bias is this small, constant nudge that fine-tunes the final dish. And the network learns both of these on its own.
Perfect summary. And that's how we move into the actual learning loop. We have our first guess at the recipe, our starting weights and bias, and we start cooking.
But a good cook doesn't just follow the steps blindly. They taste along the way.
Right. And these internal taste checks inside the network are called activation functions.
So why do we need these? I mean, if the inputs are numbers and the weights are just multipliers, can't you just use simple arithmetic to get to the end? Why these checkpoints?
That's a critical point. If it was just simple arithmetic, just straight lines, the network could only solve really simple linear problems, like calculating sales tax.
But the real world isn't a straight line.
And cooking definitely isn't. The relationship between ingredients is nonlinear. You know, adding 1 gram of salt makes it better, but adding 10 grams makes it inedible.
Ah, so the activation functions let the network handle those complex, it depends kind of decisions.
Exactly. They introduce nonlinearity. They act like decision filters. The source mentions a few good intuitive ones, like the ReLU function.
Right.
Think of it like a simple switch.
Yeah.
If the flavor profile at this stage is positive, if it's helping, we keep it. We pass it on to the next step. If it's negative, if it's making the flavor worse, we just ignore it, set it to 0.
So it's not just math, it's the network actively deciding, is this information useful or should I just drop it?
Precisely. And you have others like the sigmoid function, which is great for simple yes-no. Is this dish acceptable or not?
Or ton.
Ton, which puts it on a scale from very bad to very good. These little checks make the whole system dynamic.
Okay, so we've moved through all these internal checkpoints. The cook follows the whole recipe, boiling, mixing, all of it, and produces a final dish.
Yeah.
That entire process is called forward propagation.
It's the execution. You're using your current recipe, your current weights and bias to make the dish.
And then comes the moment of truth, the taste test. And that taste rating, that score, is the loss function.
Tastes awful. That's a high loss score. Tastes almost perfect. Very low loss. The loss function just turns the result into a number. It tells us how far off were we from our goal.
And what's really important here is that loss is just feedback. It's not criticism. If the dish is terrible, we don't just throw it out.
We immediately try to figure out why it was terrible.
Which takes us to the truly revolutionary idea of backpropagation.
Backpropagation is the network's way of thinking backward.
Right.
If the loss function says the dish was way too salty, the cook needs to figure out which specific step, which ingredient was most responsible for that.
So how does it assign that blame? If you have, 50 different weights for 50 ingredients, how does it trace that high loss score all the way back to the one specific weight that caused the problem?
It's a really elegant bit of calculus, but the intuition is simple. It traces the error backward, step by step, and calculates the blame assignment for every single weight and bias.
So it figures out how much each one contributed to the final error.
And more importantly, it calculates exactly how to change each one to make the error smaller next time.
So it's not just, this is too salty. It's, we need to reduce the salt weight by 0.05 and maybe increase the herb weight by 0.01 for the next try.
Exactly right. And that leads us to the very last piece of the learning loop, gradient descent.
So if we know the dish is too salty, why not just, slash the salt weight vast right away? Why do we need this gradual process?
Because if you make a huge drastic change, you might just overshoot the target completely.
Oh, right. You go from way too salty to instantly too bland.
And your training just becomes unstable, flipping back and forth between extremes. Gradient descent prevents that.
So we're trying to find the lowest point of error, the perfect recipe, and gradient descent is like walking down a hill in the fog.
That's the classic analogy. You take small, steady, calculated steps in the right direction. And that small refinement, repeated millions of times, is what actually perfects the recipe. It ensures stable, gradual learning.
So that whole loop forward propagation to get a result, the loss function to score it, back propagation to assign blame, and gradient descent to make tiny adjustments, that's the entire engine of deep learning.
That's it. It's just practice and feedback turned into math.
And that learning only happens because those parameters, the weights and bias, are allowed to change automatically.
But there's a second really crucial level of control that people often overlook. It sort of sets the boundaries for all of that learning.
Right. So we have the parameters, which the system learns on its own, but then we also have hyperparameters, What's the difference?
The crucial difference is who decides them and when. Parameters, like we said, are learned through practice. The network figures out the perfect amount of salt on its own.
Okay.
Hyperparameters, on the other hand, are decisions you, the human, make before the learning even starts, and they are never adjusted automatically by the network.
So the human is basically designing the kitchen, not deciding on the specific ingredients.
That's a great way to put it. Hyperparameters are things like how many layers the network has, and so how many internal taste tests the cook gets.
Or the cooking temperature, or how many times the cook is allowed to try the recipe.
Exactly. Those choices define the limits and the speed of the whole training process.
That distinction is fascinating. So the model learns the ideal amount of salt, that's a parameter, but the human chooses to use olive oil instead of butter, and that's a hyperparameter.
Yes, and that choice you made up front, olive oil versus butter, fundamentally constrains the kind of flavor profiles the machine can ever discover on its own.
So your upfront decision about the process actually defines the ceiling of the system's potential.
It absolutely does.
So what does this all mean for you, listening to this? We took something that sounds incredibly complex, a neural network, and we broke it down.
Into simple, intuitive steps.
Right. Prepping the data with vectorization and normalization.
Setting the influence of each part with weights and bias.
Using activation functions as those internal checkpoints, and then running that core learning loop. Loss, backpropagation, and gradient descent.
And now you have the fundamental intuition behind how these incredibly powerful deep learning models actually work. And that's essential because it lets you think critically about how these systems learn, not just what they spit out at the end.
And before we go, let's just circle back to that last point, that critical distinction we made.
The parameters versus the hyperparameters.
Right. We established that the parameters, the weights, the bias, those are learned automatically by the machine through practice.
But the hyperparameters, the initial choices about the architecture, the learning rate, the boundaries of the process, those are all fundamentally chosen by us, by humans.
Which raises a really important question. If the parameters are learned but the hyperparameters are chosen,
Yeah.
how much does that initial human decision, that setup, that initial constraint, how much does that limit or define the ultimate potential and maybe even the inherent behavior of what the machine is learning? It's something to think about as you see these generative AI systems evolving all around us.
Thank you for joining us for this deep dive. We'll see you next time.